Welcome to Cybersecurity Under Pressure. Real attacks, real lessons. I'm Antonio Gonzalez.
And I'm Sarah Chen.
Today we're digging into railway OT data and post-quantum crypto. It's complicated.
Complicated is one word. Welcome, everyone.
So this railway maintenance data, it's not being stolen to derail a train today. Like nobody is sitting in a basement right now trying to flip a switch. They're stealing it for 10 years from now.
Right, which is what people just don't grasp when they look at these threat intel reports.
Because I get stealing credit cards.
Yeah.
I get ransomware. But we're looking at threat actors hoovering up telemetry data from a train. Who cares about a failure signature from a train door? Or, wait, it just seems like an incredible waste of bandwidth.
It's not a waste of bandwidth if you understand what that data actually is.
But you're pulling gigabytes of vibration data, maintenance logs, operational patterns from a rail network. Nobody's monetizing that today. It's just sitting in some archive gathering dust.
Because that data is the DNA of your critical infrastructure.
The whole harvest-now-decrypt-later thing, HNDL, everyone talks about it like it's a spy movie. But for operational technology, come on, it's a train door, it's a brake sensor. Why go through the trouble of exfiltrating encrypted maintenance schedules?
You're looking at it like a quick flip, like a typical IT breach, but this is a long game. The engineering value of that data doesn't expire in 6 months like a stolen password.
Hold on. The coffee's dripping all over the desk.
You need a napkin or something.
Yeah, got it. Stupid lid. Anyway, you were saying the DNA of the infrastructure.
Right. Think about the life cycle of a train or a switching station. If you're managing a corporate IT network, your laptops, your servers, they get cycled out, every 3 to 5 years?
Maybe less if the budget is good.
Exactly. But operational technology, these assets are in the field for 10, 20, sometimes 30 years.
Yeah, they just sit there.
A trackside programmable logic controller, a PLC, installed in 2015 is going to be sitting there in 2035 doing the exact same job. So the engineering value of the data being harvested today will still be entirely relevant a decade from now.
But it's just telemetry. Let's break down what telemetry actually is. It's literally just a stream of numbers. The door opened, the door closed.
It's way more than that.
Well, let's look at the vibration data on a train's axle. You've got an accelerometer mounted on the bogie, and it's sending back a 4 to 20 milliamp signal that translates to the vibration on the left axle is at 0.4 millimeters per second.
Right, the raw physics.
Exactly. It's just a raw physics measurement.
Right.
What is a nation state going to do with 0.4 millimeters per second?
It's not just telemetry, it's the baseline of reality for the physical system. If you are a plant manager or a transit operator listening to this, you know that data is how you build your predictive maintenance models.
Sure, to know when to swap a part.
Let's take that exact vibration data you just mentioned. If an adversary captures the encrypted telemetry histories and failure signatures today, and they throw it on a server rack in the middle of nowhere, and then they crack it in 2032 when quantum computers mature, what do they have?
A bunch of really old maintenance logs.
They have the exact operational patterns of your rail network. They know exactly how your maintenance models are tuned.
So they know when we fix things. Big deal.
No, it's not just scheduling. They know the exact tolerances of your safety systems. If I have 5 years of your historical decrypted vibration data, I can run my own machine learning models on it.
Yeah.
I can build a perfect digital twin of your physical train in my lab.
Wait, a digital twin?
Yes. If I know your maintenance model predicts a catastrophic bearing failure when vibrations hit 0.8 millimeters per second, and I know your trackside sensors are programmed to trigger an automatic emergency braking alert at 0.6, I now have the exact physical parameters I need to engineer a physical zero day.
Oh, wow. Okay, wait. So you're saying I don't need to write a complex malware payload that buffer overflows the train's operating system.
Exactly. I don't need to break your software at all.
I just need to spoof the telemetry.
Precisely.
If I can get into the network 10 years from now, and I know the actual physical limit is 0.8, but the alarm is at 0.6, I just use a man-in-the-middle attack to feed the control center a constant forged telemetry stream that reads 0.5.
And the dashboard says everything is perfectly fine.
Right. The automated safety systems stay asleep. Meanwhile, the actual physical hardware grinds itself to dust, the bearing seizes, and the train derails.
See, it's not about derailing a train today. It's about having the blueprints to do it completely undetected a decade from now during a geopolitical crisis.
The physics-based zero day.
That's the real threat.
So they're building a digital twin of our infrastructure in their own labs, using our own encrypted data that they just sucked off the wire and put in cold storage.
Exactly. That's the core of harvest-now-decrypt-later in the OT space. The risk isn't just future access to some confidential payload or a CEO's
Which
emails.
is what everyone focuses on.
Right. But for OT, it is the long-term exposure of your most sensitive operational secrets, how your grid balances loads, how your rail network handles congestion, the exact failure signatures of your legacy equipment. They are mapping the physics of your system.
It's just, it's exhausting to think about. We're defending against ghosts.
Essentially,
We're
yes.
encrypting it with standard protocols today, thinking we're safe, and they're just laughing, waiting for the math to catch up.
Waiting for the math to break, essentially, which brings us to the actual mechanics of what breaks and what doesn't.
Because the industry narrative around this is surprisingly sloppy. You read the headlines, and everyone is screaming that quantum computers are going to instantly decrypt everything everywhere all at once.
Yeah, the panic is completely misplaced.
Yeah, the math. It's Grover's algorithm doing the whatever it does to the mind. It has the key space or something.
It effectively reduces the security level by half, yes. But here's where we need to be incredibly precise, because people are panicking about the wrong things.
Okay, lay it out.
Let's unpack the cryptography. We have two main types, symmetric and asymmetric. Grover's algorithm affects symmetric cryptography. Algorithms like AES, the Advanced Encryption Standard.
Right. And symmetric crypto is the heavy lifter. It's the vault.
Exactly.
If I have a massive file of vibration data, I encrypt it with a single AES key. I use that key to lock it, and you use that exact same key to unlock it. The standard today is AES 256, meaning the key is 256 bits long.
Which is incredibly secure.
Right. There are 2 to the power of 256 possible keys, which is, I mean, it's roughly the number of atoms in the observable universe.
But massively huge.
So even if a quantum computer uses Grover's algorithm, and as I understand it, Grover's doesn't just guess blindly, it uses quantum superposition to evaluate multiple probabilities simultaneously, which effectively cuts the search space in half.
Yes, that's the mechanical effect.
But having a 256-bit key still leaves you with 128 bits of security, which is still 2 to the power of 128. I mean, good luck brute forcing that even with a quantum machine anytime soon. The sun will burn out before you crack 128 bits.
Precisely. The technical nuance here is critical. AES 256 is still widely regarded as practically robust against quantum attacks.
So AES 256 is fine. The payload is safe.
The payload itself, yes.
Which is exactly why people are going to ignore this whole thing. They'll look at their IT policies, they'll look at their payload encryption, see AES 256 checked off on the compliance sheet, and say, cool, box checked, we're quantum proof, the telemetry and cold storage is safe.
And that is exactly how the entire trust architecture collapses. You can't just look at the payload.
But the payload is what's encrypted. If the AES key holds, the telemetry is safe in the vault.
How did the AES key get there?
Well,
Think about it. How did the train's endpoint and the control center server agree on that specific AES 256 key over an open monitored network?
right. They have to exchange it first. The asymmetric stuff.
Yes. They used public key cryptography, key establishment protocols, certificate chains, digital signatures. That is the massive exposure.
Okay, let's break this down for the listener, because this is where the wheels come off. Public key infrastructure, BKI.
The Achilles heel.
Asymmetric cryptography.
Yeah.
This is RSA, or elliptic curve cryptography, ECCC. This isn't locking a vault with a single key. This is math based on prime factorization.
Correct.
I generate a public key that I can share with the whole world and a private key that I keep secret.
Right. And the security of RSA relies on a very specific mathematical asymmetry. It is trivially easy for a classical computer to multiply two massive prime numbers together to get a gigantic composite number.
Like doing basic multiplication.
Exactly. But if I just give a classical computer that gigantic composite number, it is practically impossible for it to work backward and figure out which two prime numbers created it. That's the trapdoor function.
Until Shor's algorithm enters the chat.
Yes. Peter Shor, back in 1994, figured out that a quantum computer doesn't need to try dividing the massive number by every possible prime, which is what takes a classical computer millions of years.
So it takes a shortcut.
Shor's algorithm uses quantum interference to find the period of a function, basically finding the underlying repeating structure of the numbers.
Right.
It turns prime factorization from an impossible exponential problem into a very solvable polynomial problem. Shor's algorithm completely breaks the mathematical foundations of RSA and elliptic curve cryptography. And those are the protocols that secure the identity of the devices and facilitate the secure exchange of those symmetric keys.
So if I'm a trained maintenance gateway, and I'm sending my encrypted telemetry to the control center. The data itself is locked in that AES-256 vault. The vault is solid. But the courier who delivers the key to the vault...
The courier is using a fake passport. Let's look at the passport analogy.
Yep.
When your train connects to the server presents a digital certificate. That certificate says, I am the legitimate control center. How do you know? Because the certificate has a digital signature on it from a trusted certificate authority, a CA.
Like a government stamp.
The CA is like the government issuing a passport, and the digital signature is the holographic seal.
And that holographic seal is forged using RSA or elliptic curve math.
Exactly. So if an adversary has a quantum computer running Shor's algorithm, they don't need to hack the government to steal the physical stamp.
They just print their own.
They use the quantum computer to perfectly calculate the CA's private key just by looking at the public key. They can now forge the holographic seal perfectly.
It's an identity problem.
Massive one.
A massive one.
Okay, so if the certificates fail, it doesn't matter how strong the AES encryption vault is, because the adversary can just impersonate the control center.
Exactly. They intercept the connection, show the perfectly forged passport, and say, hey, send me the telemetry using this new AES key that I control. Or worse, they go the other way. They impersonate the train to the control center and send forged telemetry.
Precisely. They manipulate the operational patterns. They feed false failure signatures into your maintenance models today, so your engineers make incorrect calibration changes tomorrow. The whole system of trust evaporates.
This is wild.
The transition to post-quantum cryptography, PQC, is actually an identity and trust architecture problem. It is not a payload encryption problem.
But nobody talks about it like that.
We have to stop talking about it like we need stronger vaults. We need an entirely new way of issuing passports.
And this isn't some theoretical academic debate for the 2030s. The standards are already here. I was reading through the source documents, and NIST, the National Institute of Standards and Technology, they just finalized the math.
Yes, they just standardized ML-Chem in FIPS 203 and ML-DSA in FIPS 204.
Oh, great. More acronyms for the engineers to ignore until an audit. Let me guess. Module lattice-based key encapsulation mechanism and digital signature algorithm.
You got it. It's an entirely new foundation. We're moving away from prime factorization and elliptic curves and moving into lattice-based cryptography.
Which means what, exactly? If I'm an engineer sitting on the shop floor, what is a lattice?
Think of a lattice like an infinitely repeating grid of dots, but not just in 2D or 3D. Imagine a grid in thousands of dimensions.
Sounds like a headache.
The mathematical problem is called the shortest vector problem. If I drop you at a random point in this 3,000-dimensional grid, finding the closest actual grid intersection is incredibly difficult.
Okay, so it's a maze.
It's mathematically hard for classical computers, and crucially, there is no known quantum algorithm, no equivalent of Shor's or Grover's, that gives a quantum computer a shortcut to finding the answer.
Okay, so the math is solid. Regulators are looking at this and saying, we have the new math, roll it out.
It's not just audits or suggestions. The EU is already pushing a coordinated roadmap for the transition to PQC. They want critical infrastructure moving to these new cryptographic standards.
Roll it out. Right.
Yeah.
Just drop a 3,000-dimensional math problem into a 15-year-old railway switching system.
Yeah.
Have they actually looked at the specs for these new standards? Have you looked at the size of these things?
The signature sizes, yes, they are significantly larger.
Significantly larger is the understatement of the decade. I was looking at the notes on ML-DSA 65. The digital signature alone, just the holographic seal on the passport, is 3,309 bytes. 3309.
Which is a necessary trade-off for quantum resistance. The lattice math requires larger matrices to ensure the...
I don't care about the matrices. Do you know what 3D309 bytes does to an embedded gateway from 2012 running on a 9600 baud serial connection?
Well, it's heavy.
It crushes it. It's an elephant stepping on a tin can. Let's do the math for you if you're listening and wondering why this is a big deal. 9600 baud translates to roughly 1 kilobyte per second of actual data throughput. If you try to send a 3309-byte signature, it takes over 3 full seconds just to transmit the identity handshake.
Right.
You're talking about legacy field environments where every millisecond of latency is budgeted.
But if the EU is pushing... Actually, no, forget it. The latency would kill it.
Thank you, yes.
Yeah.
The latency kills the system. We're talking about operational technology, not a web browser.
True.
In a web browser, if a TLS handshake takes an extra 3 seconds because you're passing a massive quantum-resistant certificate, who cares? You stare at a white screen for a second longer before your news article loads.
Right. Nobody dies.
But in a train braking system or a power grid protection relay, A 3-second delay means the watchdog timer expires.
Right, the deterministic loops.
Exactly. These PLCs operate on deterministic loops. They expect a heartbeat ping every 50 milliseconds. If the processor is busy doing thousands of matrix multiplications to verify a massive lattice signature, or the network link is clogged for 3 seconds transmitting the certificate, the PLC misses the heartbeat.
And that's catastrophic.
When an OT system misses a heartbeat, it doesn't just buffer. It assumes the network is dead and it fails safe. It trips the breaker. It slams on the emergency brakes.
The timing-sensitive environment simply cannot process the overhead. It is physically impossible without violating the safety parameters of the equipment.
They physically can't. You've got constrained links, low bandwidth, RS-485 serial cables strung along miles of track. You have embedded processors with barely enough RAM to run their core logic, let alone store and process a hybrid certificate model doing matrix math.
It's just not designed for it.
If you try to push a 3309-byte signature down a constrained link to a legacy PLC, you are going to crash the whole segment drops offline. You cause a denial of service on yourself.
Which is exactly why blindly dropping PQC into legacy field architectures is not a serious plan. You can't mandate a patch that bricks the infrastructure.
But the regulators...
The regulators are writing policies for IT environments and hoping they apply to OT. They don't. A server farm in Frankfurt can handle a 3 kilobyte signature without blinking. A trackside sensor in rural Ohio cannot.
Not a chance.
So we have this massive disconnect. The threat of harvest now, decrypt later is very real. The vulnerability in our identity and trust architecture is very real. But the standardized solution fundamentally breaks the physical constraints of the field devices.
So we're stuck. We leave it vulnerable to quantum decryption in 10 years, or we crash the trains today with massive crypto overhead.
We're not stuck, but the answer is definitely not PQC everywhere all at once. That's the IT mindset leaking into OT.
Okay, then what is it?
We have to fundamentally rethink how we design these networks over the asset's lifecycle.
Right. Slower. Let's think about this. If the endpoint can't handle the math, but the server needs the math, so we just isolate it. Hard separation.
It's not just a switch you flip. You're talking about crypto agility, which is a lovely buzzword that vendors throw around in marketing brochures right now. But in practice, it is incredibly complex.
It just means being able to swap out algorithms without rewriting the whole software stack, right? Like having a modular plugin for your encryption instead of hard-coding RSA into the core operating system.
In software, yes. In an enterprise IT environment, crypto agility means you update a library, you push a patch, and your servers start using ML10 tomorrow.
Easy enough.
But in OT, crypto agility requires a phased migration and a brutal, honest assessment of your physical architecture. You mentioned hard separation. That's the key. Think about the Purdue model for industrial control systems.
Okay, the standard hierarchy.
You have to draw a hard line between what must stay deterministic, the level 1 systems, the PLCs, the sensors that absolutely cannot handle a 3309-byte signature and unpredictable latency, and the systems at level 3 that can absorb the cryptographic overhead.
Ah, I see what you're saying.
Think about the edge gateway.
Okay, so the sensor on the axle, the embedded controller pulling the vibration data, those stay legacy. They keep doing what they're doing.
Yes.
They maybe use lightweight symmetric crypto like AES, or no crypto at all if they are physically air-gapped within a secured trackside cabinet.
Exactly.
But the gateway, the actual communication node that talks to the outside world, that connects the train to the regional control center over a cellular network or wide area network, that's where we put the heavy lifting.
Exactly. The gateway acts as a proxy. It terminates the post-quantum connection from the control center.
Taking a hit for the downstream devices.
Right. It handles the massive MLDSA signatures, it has the CPU power to do the heavy matrix math, and it has the memory to store the larger keys. Then, on its internal interface, it communicates with the internal deterministic devices using legacy low-latency protocols. It bridges the gap.
But you're still relying on vendors to actually design that capability into the gateways. Have you looked at the OT market lately? Most of these platforms are monolithic black boxes. You can't just slide a new cryptographic abstraction layer into a proprietary system from a vendor who hasn't updated their firmware since Obama was president. The safety logic and the communication logic are mashed together on the same circuit board.
And that is the crux of the entire issue. If you are listening to this, imagine you are an operator or an engineer writing procurement requirements today.
They're just copy-pasting specs.
If your OT platform cannot evolve its identity layer without jeopardizing availability or safety, that is not only a security issue, it is a lifecycle design issue.
You're buying a life cycle nightmare.
Absolutely.
If you buy a system today where the security certificates are hard-coded into the same chip that controls the emergency brakes, you are buying a ticking time bomb.
You are buying a system that is fundamentally incapable of surviving the next decade of cryptographic transition. And the vendors know this, or they should.
They definitely know. They just want the margin.
But designing for true crypto agility, for phased migration where you can independently upgrade the trust architecture without having to recertify the entire safety system, that is expensive.
Yeah, that costs R&D money.
It requires modular hardware design. It requires separating the communication microprocessors from the deterministic microprocessors.
Which nobody wants to pay for. They want the cheapest bid that meets today's compliance checklist. And today's checklist says, does it have AES 256? Yes. Does it use standard RSA certificates for TLS? Yes. Boom. Signed, shipped, installed for the next 20 years.
But the threat model has shifted. The data being generated by those cheap monolithic systems today is already being harvested.
The telemetry, the vibration data, the maintenance logs.
All of it. The adversary doesn't care that your system isn't crypto-agile. In fact, they are banking on it.
They want it to be rigid.
They are banking on the fact that your legacy field architectures are too fragile to support FIPS 203 and 204. They know you can't push those 309-byte signatures down to the trackside equipment.
Because if we try, we cause a denial of service on ourselves.
Right. So what do? We delay the transition.
We need an extension.
Exactly. We ask the regulators for exemptions. Please don't make us implement MLDSA. It will break the trains.
And the regulators cave.
So we keep using vulnerable RSA public key infrastructure because we have no choice, which just gives the adversary more time to sit on our networks, intercepting our key exchanges, harvesting our operational data, mapping out our failure signatures.
It's a trap. The physics of the legacy systems are actually acting as a shield for the attackers.
Yes.
We can't upgrade the cryptography because of the physical constraints of latency and bandwidth, which guarantees the attackers get an uninterrupted stream of the exact data they need to build their future 0 days.
It's a severe architectural debt. And we're paying the interest right now in the form of exposed engineering data.
So what's the move?
You have to start separating the life cycle of the safety logic from the life cycle of the security logic. If a vendor pitches you a new control system and the identity layer is hard-coded into the deterministic core, walk away.
Because when the EU mandates post-quantum cryptography in 5 years, and there are no more exemptions, you'll have to rip and replace the entire physical controller, not just snap in a new security module.
Exactly. You'll be throwing away millions of dollars of perfectly good industrial hardware, rewiring crackside cabinets, shutting down rail lines for weeks, just because the math on the digital certificate changed and your CPU couldn't handle a lattice matrix.
It's absurd. But it's exactly what's going to happen to hundreds of transit authorities, power operators, and water treatment plants who aren't looking at the 10-year horizon.
They're not looking far enough ahead.
They're just looking at next quarter's budget and today's IT compliance checklist. They think because they have AES 256 on their payloads, they are immune.
Which brings us back to the stark reality of the threat and the real lesson buried in all these white papers. You have to think about the timeline of your adversary versus the timeline of your hardware. If your railway telemetry from today is being harvested for a quantum attack 10 years from now, and your hardware is designed to sit in the field for 20 years, your current lifecycle design isn't just outdated.
It's a liability.
It is actively feeding the adversary's future models. Every day you run a monolithic, non-agile system, you are handing them the physics of your infrastructure.
It's chilling.
We're letting them map the breaking points of your physical world while you are trapped behind the mathematical limits of your legacy hardware.
And no amount of network monitoring or firewall rules can save you if the fundamental trust architecture, the identity of the devices themselves, can be perfectly forged by a machine that treats prime factorization like basic addition.
Exactly. You can't outpatch mathematical certainty. You have to architect around it.
So we're screwed, basically, unless we fundamentally rip apart how we buy and design these systems.
Unless we demand modularity and crypto agility at the hardware level today. Yeah.
That's it. Go patch your systems.